Velkommen til Kunnskap bibliotek. Det er fantastisk å se så mange og så mange unge som kommer til biblioteket for å høre om været vårt, hvorfor været er som det er, og hvordan det kanskje kommer til å bli, og hvorfor. Og hvordan vi kanskje kan få det til å bli. Hvordan. Mange unge, det er deres fremtid vi snakker om, så veldig flott å se at det er så veldig mange unge som kommer. Dette arrangementet som vi har på biblioteket i dag, det er jo en del av Kunnskap til lunsj-arrangementet som vi kjører en gang i måneden her på biblioteket i samarbeid med høyskolen og fylkeskommunen. I tillegg så samarbeider vi denne gangen med Klimafestivalen, som er en nasjonal festival som foregår nå i disse dager. Så Kongsberg har liksom hengt seg på den festivalen og har dette arrangementet. Og det er derfor vi har fått seniorforsker ved meteorologiske institutt, Rasmus Benestad, til å komme hit og snakke om vær og klima. Og han representerer også Tekna Klima når han står her og snakker. Vi har fått et ønske fra skolen om at foredraget skal holdes på engelsk, og det har vi etterkommet, og det er vi veldig glad for når vi ser at det kommer så mange elever. Det betyr kanskje at det innimellom kan være noen faguttrykk dere ikke helt forstår, men da går det an å spørre. Og vi åpner også for en spørsmålsrunde etter at foredraget er ferdig. Så da sier jeg bare følg med. Og vær så god, Rasmus Benestad.
Takk, Elisabeth. Hi. Hello. I'm going to speak English. So, yes, it's nice to see so many of you here today. Climate change is about your future, but also my past. This picture here is of myself and my brother, and the third guy there doesn't exist anymore. I grew up at a time without internet, without mobile phones, Instagram or Facebook. But it was also colder then. Like we would have snow in the winter, go skiing. We wouldn't hear the birds sing in January. But we couldn't, I think nobody of us could actually predict the evolution, like how things have changed. But there was one thing that we could foresee, and that was actually indeed foreseen in the past. That was that the temperature was going to increase. And that has been done long ago. But in 1989, there was an American scientist, James Hansen. What he did, he actually used a weather model and he computed the temperatures, how they will change in the future. So how did he do that? I'll show you first his results, and then I'll tell you a little bit more of that. So here are his results, and also I'll show you what the truth is afterwards, like, you know, that he got after 89. So these were actually made before 1989. So you see that the red and the black curves are the actual observations. That was actually what happened. And then there are three lines there, green, blue and purple. And they show his results. These are the global mean temperature that he calculated. Okay. How did he do that? He used a weather model. And in that weather model, it's a bit similar to the one we use today, 4 times a day, what I use for ing.no and computer weather forecasts. But it's somewhat different as well. It has some more things into it as well. And he put in greenhouse gases into that, CO2. But he didn't know what the CO2 would, how that would change in the future. So what he did, he guessed. Okay? He made some fairly reasonable guesses. So the CO2 he put in here are shown here. So now they're a bit different color sets. So the green actually what happened when it comes to, we call it forcing, so it's not just CO2 but other greenhouse gases too, and also solar forcing and volcanoes. So you have the black line, red line and the pale blue line. So these correspond to, the black line corresponds to the green line here and red line here and the light blue line here. And he actually hit quite well with his forecast. It's quite good. Like, you know, the evolution has followed quite close to what he predicted. But we also know that we cannot more than 10 days in advance. So how can we actually compute the climate 100 years from now, or many years from now, when we can't predict the weather? Sorry, yes. I'll go back a little bit now, because I want to go back to the the climate model and say that we can, in a way, these models have been used more recently as well, or more advanced models, and the exercise has been repeated many times. And these figures are from a fairly recent IPCC report. It's from 2007. And what you can do, you can feed these models with all you think are going to affect the climate, and then you can say, okay, well, let's just give it all the things we think affect climate, but gases. So this is between the upper and the lower. So the black line here are what has actually happened, and the thin yellow lines here are the model results. And you can see the effect of volcanoes, and also the rise in temperature here with greenhouse gases. And you see what happens if you don't have greenhouse gases. You see that there's an effect of the greenhouse gases. It has caused the global warming now. And back to the weather models, because these are the weather models basically modified for climate purposes. So how do the weather relate to climate? How can we actually say anything about climate when we cannot predict the weather more than 10 days ahead? But we know why we cannot predict the weather more than 10 days ahead. And there was a guy called Edward Lorenz in 1961. He actually discovered that playing around with his weather model, he got different answers just because he used slightly different computers. Like there were some very, very tiny, minuscule differences in how he started his weather model, and he got completely different results. Why was that? Well, what he did was that he stumbled on something called the chaos effect, the butterfly effect. And here I show the butterfly here. So and this is actually what he did. He had a very simplified model. It's only has three things it predicts. So this is a mathematical shape, a three-dimensional mathematical shape. And what is typical with weather is that it seems like it's repeating. You get similar kind of weather and again and again and again, but it's never identical, and it's never in the same order. So you cannot predict exact order, what is actually going to happen at a certain time, at a certain place for longer than a few days in advance. And this is a very fundamental discovery that is actually not just true for weather models or meteorology, but it's everywhere, even in biology, and it's all over in the universe. So this chaos effect is something that he discovered with the climate models. And we know that the weather we should not be able to predict what it will be like maybe 2 weeks ahead from now. But I can say that in 6 months it will be warmer now. Here. Most likely. Why can I do that? Because I can say something about weather statistics, not the weather itself. I cannot say what the weather will be like on 23rd of June. But I can say that the probability is that it will be warmer than now, because it's summer, not winter. We know there are certain things that affect the weather statistics. And this is basically how you can present or show what the weather and climate is in terms of mathematics or statistics. So the weather is actually a condition at a certain place at a certain time, and this can be represented here. These are temperatures from Oslo. So each dot here is one temperature for one day. And what you see here is that it goes up and down and up and down and up and down and up and down. That's fairly predictable. What is that?
It's the winter and summer.
Yes, it's winter and summer, yeah. But you can also present this information. This is just a summer temperatures here. You can show it as a histogram, and I think you probably learn about histograms in school. At least my kids did. And it shows what is a typical temperature in summer in Blindern, and you can see here is the highest value. So this temperature happens most often, and these accounts, and you sometimes get temperatures up to 25, 20, maybe 30, but not very. It's very rare, and also very rare here as well. So this shape here is basically a smooth shape. It's a Gaussian shape fitted to the data, and the red dashed line here is a different shape. It's like when you have a climate change. It's a change of weather statistics. That's all what it is. It's caused by something in physics, but it's basically change of weather statistics, and we can predict that. And that is what Jim Hansen predicted. I want to actually bring an analogy to this, because you can also make the same claim about boiling, that I cannot predict where the bubbles will be when I boil a kettle, but I can predict they will come when the water heats up. And I can also say something about intensity, the boiling statistics. I can say actually it will start to boil more quickly in the high mountains and further down here. So we can actually do a lot of predictions. We know a lot of things even though we don't know everything. And we should also know why we don't know everything. And another thing is that if you look at the mean temperature in the world, you will see that the temperature tends to be higher in the tropics than in the polar regions. There's actually a very clear latitudinal dependency of the temperature. And this figure here shows basically that the mean temperature is the sum of these two. So this is how the temperature, this is the average temperature for each latitude. So you see it's the warmest in the tropics, and it's very cool down here in Antarctica, and also the North Pole, but not quite as cold. Remove this latitude dependency from this picture here. You get this here. This is what is left here, and you see that there are also other things that determine the temperature, the mean temperature. And in Europe, we are very lucky, because in Europe the mean temperature is between 5 and 10 degrees warmer than the average on our latitude. And why is that? It's because of the oceans, the ocean currents and the winds. And also you can see that, like here, where you have the high, like in high latitudes, high places also it gets cool as well. So a lot of things we know that do affect the weather statistics. And we also know that other things affect the rainfall statistics, how far you are from the oceans, and also if you're on the shadow of the mountains and so on. So we understand a lot about climate and also the weather. Another thing is that if you just look at not just the mean climate, but also how it changes, the climate variations, because you have year to variations, you have maybe variations from one 10-year to the next decade. We know that a typical picture, this is actually the temperature from central England, and it's from 1650. That's the longest time record we have of temperature in the world. And you can see that it changes. So that is a typical the picture. And we understand why that happens, and I'll actually tell you why. But before I do that, I want to tell you about a Norwegian guy. I don't know, very few people actually know about. He's called Jakob Bjerknes. He was son of Wilhelm Bjerknes. He was the sort of father of meteorology at Bergenskolen. He was one of the guys who started the modern meteorology, weather forecasting. And he discovered that what we call it a linear southern oscillation. So there are two phenomena. It's the El Niño that people knew about long ago, that the coastal waters outside Peru and Ecuador sometimes was warmer than normal. The fishing sort of died off because the fish died. And it's called El Niño because the people who lived there were Catholic, and it happened around Christmas time, some years, but not every year. And then the southern oscillation that was actually discovered by Gilbert Walker. He tried to explain why the monsoon rain in India sometimes failed and didn't fail. It's because of the pressure difference between Darwin and Tahiti in the Pacific. It sort of swings. And he found out these were connected, these were coupled. It was like a tango between the sea and ocean. So the winds push ocean, and ocean, they warm in some places and colder in some places. They give heat off and energy to the atmosphere, create convection clouds, which again bring new winds. The trade winds will collapse, and it will actually affect half the world, most of the tropics, but not Norway. It has a profound influence on the economy, but it's also both irregular and regular. And why do I say that? Because every time it happens around Christmas time, usually. So there are some exceptions. And also the pattern, the spatial pattern, it's very much the same. It sort of warms up around this area here. That's sort of the fingerprint of El Niño. But it's also irregular because we don't know which year it will take place. Some years you will have an El Niño, sometimes you don't have one. And it's actually very hard to say why and how. And it's probably something to do with the butterfly effect. It's like the chaotic effect and longer timescales. But it affects the rainfall and temperature around the world. And also it's connected to the monsoon. That's why the El Niño southern oscillation. We understand why the monsoon happens. It's a large-scale sea breeze because during summer, when the sun starts to shine on, say, India, the continental land area, what happens? The land warms up faster than the ocean. And the land will warm the air above it. And warm air, what does that do? It rises. It's lighter. And when it rises and goes up, you get convection, you get clouds, you get rain. But it's sort of what is below, or where it was, something has to fill in because it can't be empty. So you get more air coming in from sea. So you get a large-scale sea breeze, and you also get the same thing in Norway too. And that explains wet and dry seasons. Actually, in the tropics, you don't have winters. You don't have summers. You have wet and dry seasons. So you have a very different type of seasonal system in the tropics. But we understand why this happens. And sometimes it's sort of a strong monsoon, sometimes it's not a strong one. And it sort of is connected to both El Niño and other effects as well. So our planet or our atmosphere is governed by unsettled conditions, unstable conditions. And the reason for that is that the Earth gets most of its energy in the tropics near equator because the sun's straight above you, and it gets less energy in the polar region because it comes in at an angle. And what happens is that if you look at how much energy the Earth loses back to space, because there has to be a balance between how much it gets and how much it loses, otherwise it will just warm up. It has to be stable. Then it loses more energy in the polar regions than it actually receives from the sun there. So it actually comes from the tropics. It comes through winds, it comes from ocean currents, and also from, say, jet streams. And if you look at this picture here, what do you see here? You see the Earth. I know that. But if you look closely, you see that there's a band of clouds along the equator. Why is that? It's because that's the warmest area in the world. And the air rises up and condenses, you get clouds, you get lots of rain. You get much more rain in the tropics than you get anywhere else in the world. You also see here, you see a storm system. This is, you can see also like the wind, the clouds tend to be sort of drawn by the winds as well. So the winds go at an equator, go from east to the west, and here go from west to the east in the high latitudes. And it's a way of moving the energy around the planet. And that is why we get all these changes in all the weather. And also, I want to show you this picture here. This is a jet stream, because the air doesn't like to mix very well. Sometimes maybe you've seen a river, like you can see that even the water doesn't mix very well either. And you have the polar air, which is cold and dry, and then you have the air sort of pushing from the lower latitudes, and you get frontal systems between it, so you get strong winds in these fronts when it meets. And also you get jet currents, and these actually govern the low pressure and high pressure regions. This jet stream is high up This is what is being used by the planes when they fly, because they try to utilize that to save energy, fuel. But also the storms tend to be created along these jet streams, and they lie like a snake around the polar regions. They move and meander, but it's very difficult to say how exactly they will do so in the next week or so. This is also what explains why you get some blocking highs and or in the summer. That's the trade wind. This is like when you have an El Niño, then the trade winds actually turn around and go the other way around. Also, you have heat from the oceans are important, as we saw, and wind stress on the ocean. Also, the Earth makes a difference because it sort of makes the movement curve, and it also determines how the winds actually move, and makes it more complicated and much more chaotic. So just an example here from our region here, we have something we call the North Atlantic Oscillation, and it's basically the mass of air above Iceland and the Azores is sort of like a wave that sort of slush back and forth, and that controls the pressure, because the pressure measures how much air you have above you. And the North Atlantic Oscillation, that controls the storms, how many storms we get, storm tracks. In the winter time, if the NAO is active, you get a mild winter. If it's inactive, you would get a cold winter. Here is actually a picture of Storm Berit, and it shows you how it's a sort of mixture between where the fronts meet and it sort of curl up, and also you have a low pressure here. And what you can do is that these things actually move every day, or they move along with the flow, with the winds. So you can actually track them where they are at different times. So once you do that, you can make these paths there. So these are storm tracks. And what you see is that these storms tend to cluster around certain areas. They like Iceland, they like the North Atlantic. That's where they tend to be, but not so much like further down here. So it's a sort of storm climate. It's also determined, and this has a lot to play an important role for the temperature and rainfall in our region. And then we have another type of changes here, and that is this here. Do you know what this is? Have you seen it before? It's called a Keeling curve, and it shows the amount of CO2 in the atmosphere. It's measured at Hawaii, which is far away from the sources, and you can see that from 1958 till present it has continued rising. You can see like one wiggle each year, because there's an interaction between the vegetation and the atmosphere when it comes to CO2. So the vegetation takes more CO2 from the air during summer when things grow and so on, and in the autumn when the leaves fall down and things die, it sort of releases back to the atmosphere. But why is CO2 so important? What happens? It's a greenhouse gas, yes. But what actually does happen? What is the greenhouse effect? The greenhouse effect is actually not a bad thing, it's actually natural. Without it, we wouldn't be here. And CO2 is not the main greenhouse gas, it's just one that increases. But I want to tell you something about the greenhouse effect that may be a little complicated than the story you heard before. What actually does happen? The greenhouse gases, they make the air opaque. You know what that means? It means that the light, if you shine on it, it will stop. It doesn't go through the air. They sort of stop. It's sort of absorbed by the air. It's like if you look in the fog, you don't see very far, because it's sort of the light that you receive, it sort of stops. So we also know that light is pure energy. And the light or the energy that we get from the sun is far away, so that light has to travel through space. And what is space? It's nothing. It's just vacuum. Okay. And there's one thing that we learn in physics, is that there's only one form of energy that can travel through vacuum and space. What is that? You see it every day.
Light energy.
It's light, yes. And also that means that the heat loss, the energy that the Earth loses to space, also had to be in the form of light. But it has a different color. It's a light that our eyes cannot see, but it's still light. Our eyes are not designed to see that light. It's called infrared light. It's something you use to control the TV with and so on. It's heat. You can also feel it. If you have a fire on the oven, you can feel it like, you can feel it with your hands. You can also put your hands together, and you can and if you put your hands together, you can actually feel it's warmer, because you can feel the heat. You can feel it, but you can't see it. But because the air is opaque to that light, the heat loss, which is that light, has to happen high up in the atmosphere. Because otherwise it's just absorbed by the air above, and it sort of things happen, and then it's sort of at the top of the atmosphere where there's no more air that can absorb it. That's where it sort of is able to go into space and get lost. Okay? And that's another thing we know, and people have known for hundreds of years, it's a classic physics, is that this light is controlled by the temperature. And you can actually see that if you make something really, really hot, for instance black metal, if you heat it enough, it gets red hot, it gets glowing. Because the heat, it gets so warm, it also makes it more visible as well, and even hot, it even gets white. So this temperature, at that point where the Earth loses its energy, is key to how much heat loss, or how the balance between how much energy we get in from the sun and how much that the Earth loses. And basically, it should be the same, so we don't get too much. Otherwise, it will heat up. So, this temperature is determined by two things. And what is that? That's one thing is the distance from the sun, because the light gets dimmer and dimmer the further you go away. And this is true for all the planets in the solar system, not just the Earth. And the other thing is how bright a planet is, how much of the light is sort of reflected before it gets into our system, sort of just bounces off. So these two things determine the temperature. And this is called emission temperature. And I'm going to show you a schematic how that works. So here you have the sun shining in. The energy input is at the surface, but here the energy is lost. So you see, it's lost in a different place to where the input is. But there's something that happens between the surface and here, because energy is like water. It has to flow. It cannot stop, it cannot disappear, it cannot sort of appear so suddenly. It has to flow like a river. So it has to flow from here up to here. But it can flow in different ways. It doesn't have to be light anymore. It is not just light. It is light, but something else as well. One of the most effective way of taking energy from this place up here, where it can be lost to the atmosphere, is by evaporating water. And then we have moist and warm water is lighter than dry and cold air. It will rise. You get clouds, condensation, and that releases heat. And then it actually takes energy from here, moves it up here, and then it disappears to space. But we know something else as well, and this is something the meteorologists use every day. And you know that too. The temperature the drops with height. The further you move up, the colder it gets. You can feel it when you go up in the mountains even. And there's a reason for that. It's called a lapse rate. It's shown here. Is that if the temperature is too hot and down, it will move up, and also because you get this shape because it's also heated from below. So this is what a stable atmosphere looks like. It is cooled. It's warm at the surface and cools to that temperature that determines how much heat you get when the Earth loses its heat. So what happens is that, we'll play that again, when you get more greenhouse gases, you don't see that far into the atmosphere. It's like looking down into the sea. Some places you can see the bottom when the water is very clear, and sometimes where it's murky you only see like very, very shallow layer. And that's where the light that reaches your eyes comes from. And same here. So when you get more CO2, that means that the altitude, the height where the Earth loses its heat, is moving up. And then we know that that temperature has to be the same because it still loses the same amount of heat. But also that the temperature has to drop the same way, otherwise it will move around, it will not be stable. So that means that while this moves up, then the temperature on the surface moves also higher, it increases as well. But in addition to that, you also get more changes in the winds, you get changes in the hydrologic cycle. The hydrological cycle and the greenhouse effect are like Siamese twins. So you get not just warmer, you get more rain. Changes in the rain, you actually get both more or less. So that's a little bit more complicated sort of version of the greenhouse effect, but I think it sort of completes the picture rather than just having a blanket. And this picture here shows what you would see if you were an alien floating out in space and you had eyes that only could see the infrared light. This is actually from the satellites, and you can see the heat loss from the Earth. And in areas where you have deserts and not many clouds, you see that the heat comes from further down in the atmosphere. And you can see in the areas where you have lots of clouds, here, deep clouds, they come from the top of the clouds. So you can see that the clouds do play a big role when it comes to the greenhouse effect on our climate. So the increase in the greenhouse effect, that will result in that you get an accumulation of heat, but most of that heat doesn't go in the atmosphere or the surface, but most of it goes in the sea. So 90% of that heat goes in the oceans. It has a huge heat capacity. And there's been a question or some discussion whether the temperature the warming has stopped. There's been a hiatus. And I say no, that is wrong, because you have better indicators of the state of a climate than just the global mean temperature, because the global mean temperature that we have doesn't measure the temperature everywhere. Because we don't have thermometers up in the Arctic so much, or the North Pole. We don't have thermometers everywhere in the Antarctic or in the southern Pacific. So it only measures the temperature where we have thermometers which are not evenly spread, and we know it doesn't cover the place in the Arctic where the warming is happening the fastest at the last decades, like in Greenland, and also where we see the melting of the ice. So it's much better to look at the sea level, because we know that when the water gets warmer, it expands, and also when ice melts and run down, they will also increase the sea level. We see that the glaciers melt as well, and then we see that basically the sea level rise is fairly steady. It's actually increasing. You don't have any flattening off at all. And actually, you can explain why you see the flattening off in the temperature record because it has something to do with El Niño, but also that the heat has gone down into the sea, and deep seas. You also expect some kind of some natural variations as well. So, but could there be other reasons for the global warming? So we can look at other candidates that we think, well, we know that play a role. For instance, the solar activity or the state of the sun. So these two curves here, the red one shows the temperature from NASA GIS, and the green one shows the greenhouse gases. And then I can compare them to three different indicators of a solar activity. So one is the cosmic rays here. There's a grey one here. I multiply them by -1 because they go in antiphase, so that you can see that they follow the same 11-year cycle as the sunspots, because we know the sunspots vary in the 11-year cycles. That's been known for since, well, 17th, 18th century, I think. And also then the blue line here is called the total solar irradiance. It's basically a measure of how much energy the sun outputs or produces, so that comes out of the sun. It's the sun's brightness. And what you see here is that you have all of these have 11-year cycles, quite clear. And there's no 11-year cycle in the temperature record. And also you see that all of these are full of they are actually on the same level. There's no long-term trend. There's no long-term increase. They're all on the same level. Whereas here we're talking about global warming. You see that the level is changing all the time. So and we also see other patterns, other fingerprints of the greenhouse effect, and we see we don't see such a fingerprint of solar warming in the climate. So we can be fairly sure that the global warming is not due to solar activity. And we can also see that if you look at the past, further back in time here, we see that the current warming is quite special. It's actually faster than it has ever happened before. It's actually further up here now. It's not completely up to date here. But we can see also, like in the past there, like the picture is a bit more, it's not as clear as present because we didn't have all the instruments then. We didn't have all the thermometers. So you had to try to calculate what the temperature was based on tree rings or sediments in the ocean, seabeds, and various different other evidence that we can find, because we know the climate affects different parts of the Earth system. And then we can also go back to what Jim Hansen did, these models. We can use more sophisticated models, better models, because now we also have much stronger computers, much more computer power, and we can do the same exercise again, try to calculate what the global mean temperature will be like if we continue emitting greenhouse gases. So this is from the recent IPCC report, and there's many different models there. And you can see there's a cluster of results. So in 2050, you can expect between 1 and 2 degrees higher, according to this, if we keep emitting the amount of greenhouse gases as we do. But we don't have to do that. We can actually, there are many solutions we can actually get energy away. So it doesn't have to happen that way. This is just if the greenhouse gases just increase. So I want to this is actually my last slide. Before I finish off, I have some recommendations for further reading. And there's one book I will really recommend. It's by Spencer Wirt. He's a science historian for the American Institute of Physics, called The Discovery of Global Warming. And he tells a story about the knowledge, why we know the things we know. And it's really fascinating. He sort of takes the story into the Cold War and explains why we actually we started measuring isotopes and how we can date the water, and say how old the water is, how long ago it has been before it was at surface. And there are many puzzles here which I haven't actually explained here, which are part of this story. And also there's 2 blogs there. One is called Real Climate and Skeptical Science, that are also useful if you wonder about things. You can use the search engines to look up things here. And also, before I finish, I'd like to say that I'm the Technoklima, and Technoklima have taken over a project called Klimatoppmøte i skolen, at videregående skole, where the students have a sort of role play in terms of negotiations, climate negotiations. And there's a website for that as well, and it's like an intro for that. And also we organize for realfaglærer. So that will also be, I think, 2 meetings this year. There was one last year in Oslo. I think there will be one in Bergen. I can't remember exactly where it will be. And when it will be, but it will be announced. And that's all, I think. So if you have any questions, please ask, don't be shy.
Og siden Benestad jo norsk, så går det faktisk an å spørre på norsk. Dere behøver ikke å grue dere til å formulere spørsmålene på engelsk, så bare kjør på. Ja, da var det spørsmål.
Ja.
Jeg tar det på norsk, ja.
Ja, greit.
Jeg tar det på engelsk, men det vel lettere å forstå kanskje hvis det på norsk.
Det går fint.
I klimadebatten nå så registrerer man at det noe dialog da, om med den nye rapporten som kom fra FNs klimapanel, så blir det fortsatt stilt spørsmål ved gyldigheten til hvorfor dette den eneste sannheten som man kan påberope seg da. Og en ting som jeg I hvert fall skulle ønske et klart svar på, det sammenhengen mellom CO2 og temperatur. Fordi man blir stadig vist grafer der CO2-konsentrasjonen øker, og det korrelert med økning I CO2-konsentrasjon. Og da har jeg egentlig to spørsmål. Det ene hvordan kan man vite at det CO2-konsentrasjonen som fører til økning I temperatur, og ikke at det temperatur som fører til økning I CO2-konsentrasjonen, siden temperatur kan påvirke hvor mye plass som kan løse vann. Det det ene. Og det andre, det de viste på en planke at det var en sammenheng mellom CO2-konsentrasjon, hvis det var det som var målingen på Hawaii, og solflekkaktivitet. Og solflekkaktivitet.
Ikke solflekkaktivitet.
Ikke det?
Nei, temperatur.
Temperatur, ja?
Ja.
Ja, ok. Jeg synes det var sunspot, den
Den?
Den blå...
Den?
De punktene, svarte punktene.
De grå, ja. Det kosmisk stråling.
Åja, ok.
Ja.
Da misforstår jeg figuren. Da tenker jeg det siste spørsmålet.
Ja.
Men det CO2-temperatur da?
Jo, det et godt spørsmål. Det slik at CO2 blir påvirket av havtemperaturen. Men vi vet også at temperatur blir påvirket av CO2, for det kan vi måle både I laboratoriet, og det også det vi forstår ut fra kvantefysikken. Altså, hvis det ikke hadde vært slik, så hadde hele vårt verdensbilde falt sammen. Og mye av vår teknologi bygger på det. Da hadde ikke mobiltelefonen fungert og sånn. Det veldig fundamentale fysiske lover. Det en ting, men så vet vi også at CO2 den øker, og den øker både I hav og I atmosfære. Det en av de tingene som kanskje jeg ikke nevnte, som også en bekymring, at havene blir sure, og det også har en påvirkning på økosystemene, på skalldannelse. Så vi ser jo helt klart at det går mer karbon eller CO2 både inn I havet og I atmosfæren. Cirka 40% blir hengende I atmosfæren, resten går I havene. Og så kan vi se på andre ting, for vi vet at når vi forbrenner karbon eller fossile kilder, så skaper vi CO2, da binder vi sammen oksygen og karbon. Og det vi ser at hvis vi tar forholdet mellom nitrogen, som ca. 70% av atmosfæren oksygen, så ser vi at det forholdet går ned. Akkurat som vi forventer ut fra kjemien, hva vi forventer var kjemisk, og budsjettet av masse. For det vi gjør, når vi tar fossile kilder, så tar vi karbon som har ligget millioner av år et sted borte vekk, opp og slipper det løs. Og det får vi, og vi gjør det på forskjellige måter. Det veldig mange forskjellige fingeravtrykk som viser at CO2 helt klart. Og det også, man kan spørre også, hvordan måler vi CO2? Vi måler faktisk den mikroskopiske drivhuseffekten hvor vi lyser innenfor stråling gjennom luftprøver, så ser vi hvordan det fanges opp. Så alt det henger helt godt sammen, mens derimot solaktivitet, det så mange ting som spriker, altså det ukonsistent. Vi ser at solaktivitet har en viss betydning, fordi vi ser at klimaet følelser for veldig mange ting, og derfor vi har disse variasjonene av været hele tiden. Men altså, CO2-en en rykende pistol. Altså, det bare det ikke noe tvil. Så, og det ikke bare IPCC. IPCC bare lite. Altså, vi har hele. Altså, det et kjempestort vitenskapelig miljø som enige på dette her. Altså. Ja.
Jeg skjønner jo det at det en sammenheng mellom CO2-konsentrasjon og temperatur.
Ja.
Men det jeg spør om for det sies jo at det økning I CO2 som fører til økning I temperatur.
Ja.
Hvordan kan vi være sikre på at det ikke økning som fører til økning I CO2?
Nei, for vi kan ikke forklare økning av temperatur på noen annen måte enn økning i CO2. Og vi vet at det går begge veier, det litt mer sammensatt. Og når havene blir varme, så forventer vi også at det vil slippe ut mer gass etter hvert også. Og det jo ikke bare CO2, det også vanndamp, og det mange andre ting også som har noe med det å gjøre. Men drivhusgassen velforstått. Altså, det forstår vi. Vi kan også for eksempel se på Venus, der har ikke noe hav. Masse CO2, den koker, den mye varmere enn Merkur, selv om den dobbelt så lang fra sola. Vi ser det på alle de andre planetene, så bildet helt konsistent, det ikke noe problem. Det som problemet at det noen som prøver å skape tvil som ikke berettiget, som ikke legitim. Og det disse klimarealistene. Og de folk som egentlig ikke kommer fra faget, som kommer fra andre steder, som tror at de vet noe bedre enn andre, fordi de er professor, men de bomma, ja.
Det et spørsmål til som kommer gjerne også har blitt framholdt som et argument for at CO2 neppe kan være en så viktig parameter.
Ja.
Det sier. Det det at du nevnte det at drivhuseffekten som siden i en bok, hvor lyset skal passere når du stopper da.
Ja.
Du tolker det som et eksempel.
Ja.
La oss si at det blir så mye, eller det har blitt hevdet at konsentrasjonen av CO2 i atmosfæren nå så høy,
ja.
At mengden med IA-stråling som reflekterer tilbake til jordkloden vår, den allerede metta. At ikke en økning vil føre til noe mer da.
Ja, det også misforståelse, det derfor jeg viste den her, for det som kun det som betyr noe hvor høyt hvor det nivået skjer, hvor du har hvor jorden mister varme. Og det betyr ikke noe hvor mange ganger absorberes her. Om det mette her har ingenting å si. Det et misforstått argument som egentlig vi ikke har tatt godt nok tak i. Og vi kan regne på det, altså modellene, og det validert, eller man har sammenlignet med observasjoner og satellitter. Vi har så mye instrumenter, så gode utregninger. Vi kan kjøre labmåling, vi kan teste dette ordentlig grundig testet ut. Vi bruker disse samme modellene for værvarsling. For noen år siden så fant man ut at hvis vi la til CO2-en, og CO2-økningen, så får vi bedre værvarsel også. Vi bruker disse samme modellene til sesongvarsling og lager prognoser for El Niño som treffer ganske godt. Så dette noe vi vet begrensninger, men vi vet også hvordan ting henger sammen, og vi vet at de svarene de påstandene, de feil. Ja. Ja.
Jeg bare lurer hvis det blir mer sånne CO2-gasser i atmosfæren, og de reflekterer solstråler, vil ikke det også føre til at det kommer mindre solstråler inn?
Jo, så CO2 reflekterer ikke solstråler, de slipper det gjennom. Så poenget med drivhusgassen at de slipper gjennom sollys, men ikke varmestråling. Men det en del andre partikler da, som kan reflektere solstråler, og det ser man på vulkanutbrudd og ved skyer, så det en del. Så der det bare en veldig fin balanse, og det riktig at det påvirker forskjellige veier. Men CO2 derimot kun ved varmestrålingen, ikke synlig lys. Men det som viktig at CO2 i atmosfæren flere hundre år, mens vanndamp, den faller ned da, som regn. Så den holder seg der kanskje noen dager, så faller den ut. Så den går mye fortere gjennom da, systemet, eller syklusen, mens CO2 en veldig langvarig prosess. Ja.
Det sånn at skyer reflekterer sollys.
Ja.
Vil det si at når vi da får mer skyer etter hvert, når det blir fordampet mer, at mindre sollys vil slippe inn, ja. Og så vil det bli litt kjøligere? Det
kan skje, ja. Men det kommer litt an på også hvor skyene, om det høye eller lave skyer også. Lave skyer kjøler, mens høye skyer de med på å fange opp varmeutslippet. Men så skyene den store jokeren da. Der det fremdeles en del usikkerhet, så vi vet ikke helt hvilken vei det går. Og de forskjellige modellene gir forskjellige svar når det gjelder skyer, og det derfor det også er litt forskjellige når det gjelder oppvarming. Men jeg begynte min karriere med å fly gjennom skyer og måle dem. Det ikke enkelt. For en skydråpe den 1000 millimeter, og skal fly gjennom et fly som går kanskje 200 meter i sekundene, og skal prøve å måle disse tingene. Det ikke så lett. Og så pluss at instrumentene blir våte, så man har en viss følelse for hvordan ting henger sammen. Vi klarer tross alt lage værvarsler. Ja.
Og et siste spørsmål som kanskje helt nytt for deg, det klimaendringenes betydning for læring. Årsaken at du får stadig klager på dårlig luft i klasserommet.
Ja.
Og jeg har målt en del CO2 rundt omkring. Og i de grafene dine så begynte CO2-målingene på rundt 250 ppm.
Ja.
Og prediksjonene jo ganske formidabel økning da.
Ja.
Vi vet at konsentrasjonsnivået i et klasserom synker betraktelig hvis vi kommer over 600 ppm.
Ja.
Og hvis det er over 1000 ppm, da sitter alle og gjesper og ber om pause. Det fare for at vi kan gå på en sånn konsentrasjonssmell blant menneskene?
Det er et godt spørsmål. Det finnes en YouTube-film som viser CO2 i atmosfæren som egentlig veldig interessant. Det viser at mesteparten av CO2-en i nærheten av kildene over landområdene. Og det svarer også litt på det spørsmålet tidligere, hvor kildene Og da ser vi at i sørlige hemisfære så det mye mindre enn og så varierer det med årstiden også. Så det avhenger litt av vind, hvor det blåser hen, og hvor du egentlig. Så det beste kanskje dra til for eksempel sydlig hemisfære midt ute i havet, så det ikke så stor fare for det. Ja, det er helt riktig at CO2 det gjør deg sløv, og det veldig, ja. Men vi har ikke forsket på det. Ja.
Jeg vet ikke om dette litt på siden kanskje, men vi hører om ekstreme store nedbørmengder.
Ja.
Hyppigere og hyppigere. Det noen sammenheng med den effekten der og det du her har snakket om?
Ja, det er det. Ja. Fordi at når det blir varme så øker fordampningen mer, og så får mer vann som går gjennom systemet, eller som går opp i luften. Og hvis det bare blitt der, så har man fått masse vann på enda sterkere drivhuseffekt, så det faller ut. Så det går fortere og fortere rundt da, når det gjelder vannets kretsløp. Så det ser vi på dataene, vi regner det ut også med modellene, og vi forventer ut fra enkle fysiske prinsipper. Så det er en utfordring også for Norge, så man må tenke tilpasning og finne ut hvordan man skal håndtere det da. En risiko, ja. Ok.
Da sier jeg tusen takk til Rasmus Benestad for en interessant forelesning, og jeg sier også takk til dere som kom, og ikke minst til de spørsmålene som kom etterpå, som jeg synes var veldig mye artig og spennende og avklarende. Vel, ja.
Takk skal du ha. Så jeg tror vi går med